Okay, this is part 2 of the lectures covering non-conservative forces. We're going to specifically take a look at 2 examples here. More times than not in examples, problems, and so on, the non-conservative force that you will encounter is kinetic friction. Every now and then you'll encounter a situation that involves a manual pushing or pulling type of force, but usually you'll encounter kinetic friction as the non-conservative force. Let's take a look at 2 problems involving kinetic friction here. Okay, here is once again a variation involving the incline with friction, but in this case we're going to have the object initially slide up the incline, just as a variation. So let's go ahead and take a look at the example, copy it down into your notes as I read it here. Okay, so a mass slides up an incline with an angle of inclination equal to 30 degrees and a coefficient of kinetic friction equal to 0.3. If the mass comes to rest after undergoing a vertical displacement, that's the height change of 1 meter, find the object's initial speed at the bottom of the incline. Okay, so let's go ahead and draw this out. Okay, so here's our incline like so. Here's the angle of inclination equal to 30 degrees. There's a coefficient of kinetic friction equal to 0.3. And then right here is the height change of 1 meter. Okay, and then we'll start the object here at the bottom of my drawing like so with an unknown initial speed of v0. And then it ends up here like so with a final speed of 0. And it underwent a vertical displacement here of 1 meter. Okay, now we're going to need to know the hypotenuse of this triangle eventually in this problem, and the reason for that is because that's the displacement over which the non-conservative force of friction acts. So let's go ahead and find the hypotenuse here of this triangle. We'll call that delta r. In order to do so, we'll do a little bit of sine. So sine of theta equals opposite over hypotenuse. So if you cross multiply a little bit here, the delta r is then therefore h over sine theta. So this is 1 meter divided by the sine of 30 degrees. Sine of 30 degrees is a half. So then therefore this displacement delta r, the hypotenuse of the triangle, is 2 meters. Okay, now here's our expression. We have, first of all, the work done by the non-conservative force of kinetic friction equals change in kinetic energy plus change in gravitational potential energy on the right-hand side of the expression. There's no spring in this problem, so I don't have to worry about any changes in spring potential energy. And now we just start to, first of all, fill in our terms on the right-hand side of the expression, and then calculate our dot product on the left. So first of all, the change in kinetic energy. So we're going to have here a final kinetic energy of 0, the object comes to rest, and then minus the initial kinetic energy with the unknown speed v0. So the first term looks like this. Okay, and then change in gravitational potential energy. We will have a final gravitational potential energy up here of mgh, and then minus the initial of 0. Like so. Okay, and then the left-hand side of the expression is our dot product. Calculate the work done by kinetic friction. So this is where we draw out a force diagram such that we can do so. Okay, now, as the object slides up the slope, we have the following forces. First of all, perpendicular to the incline, we have the normal force. And we have the force of gravity mg straight downwards. And then keep in mind that our displacement vector, delta r, is up the slope, so then therefore opposing that, like so, is the force of kinetic friction. There's our 180-degree angle between F sub k and delta r. Okay, now let's take mg and break it up into its usual components in these incline situations, here and here like so, thereby showing the angle theta. We will need to know the normal force later on in this problem. The normal force here, remember, cancels out with mg cosine theta. So let's write that over here. Okay, now let's go ahead and set up our dot product. So the work done by kinetic friction is the dot product between F sub k and delta r. And then as I noted earlier, as is always the case when talking about kinetic friction, there's a 180-degree angle between the force of kinetic friction and the displacement vector. Cosine of 180 is equal to -1, so we pick up our negative sign here for that reason. Like so. Okay, and then the force of kinetic friction is the coefficient multiplied by the normal force. And then here's, of course, why we need the normal force. The normal force is mg cosine theta. Let's go ahead and plug that in here. Like so. Okay, so there's my work calculation. That's then what goes here in the left-hand side of my expression. Let me now complete the problem here on the lower board. Okay, so we have the work done by kinetic friction first. That's our non-conservative force. And that then equals the right-hand side of the expression. Let me clean it up a little bit. I'm going to toss away my zeros. Like so. And now what I have to do is solve for the speed v0. So to solve for the speed V naught, let's take these two terms and switch them first, algebraically. That then gives me this, like so. And then this expression right here, by the way, is an expression of the energy transfer that occurs. Basically what happens in this problem is that all the kinetic energy that we start with at the bottom of the slope turns into heat and gravitational potential energy as we slide up the slope. And now let's just solve for the speed V naught. So at this point, I'll go ahead and cancel out the mass from each term like so. And then the last steps here are to multiply the 2 to the other side and then take the square root of both sides now to get the speed. So after you do those couple of minor mathematical steps, you end up with this rather messy looking expression. Like so. And now let's go ahead and plug in our numbers and see what we obtain. We end up with a speed here in terms of meters per second. All right, so I'm going to do the parentheses first. So 0.3 times 9.8 times cosine of 30 times 2 meters plus 9.8 times 1, multiply all of that by 2, and then take the square root of all of that. So after doing the math, this ends up being about 5.46 meters per second, like so. So notice how this example basically incorporates into it everything that we have done in this unit on work and energy thus far, ultimately arriving at this one expression, that is the expression at the top. The work done by the non-conservative force of kinetic friction in this case results in changes in kinetic plus changes in potential energy. Okay, for the second example, we're going to take a look at a situation involving spring potential energy, but now we'll incorporate friction into the situation, which is a variation that we haven't seen before. So let me go ahead and do some erasing here, first of all, for this first problem, which is now completed. So let's get rid of that. All right, let me move my file here to the second example. Okay, and then copy down the example as I read it here. Okay, a mass of 1 kilogram is attached to a fixed horizontal spring. The spring constant is 100 newtons per meter, and it's on a horizontal surface with a coefficient of kinetic friction equal to 0.3. So it's incorporating friction into a problem involving the spring force. Okay, the mass initially compresses the spring a distance of 0.5 meters from equilibrium and is released from rest. How far does the mass stretch out the spring on the other side of the equilibrium position? Now, of course, if there was no friction, it would stretch it out 0.5 meters once again. However, with friction, some of the energy is going to be lost as heat. So when we eventually get to the end of the problem, we expect the distance that the spring is stretched out on the other side of the equilibrium position to be less than the initial compression distance of 0.5 meters. At any rate, however, here's how we begin to set up and solve this problem. Okay, so here's my mass attached to the spring initially like so, and we're compressing the spring. Right here's the equilibrium position. Let's go ahead now and draw in the surface like so, because friction with the surface is important. And then we have the following values. We release the object here from rest. So first of all, the mass M is given to us as a kilogram. The spring constant K is 100 newtons per meter. Okay, the coefficient of kinetic friction between the object and the surface below is 0.3. Okay, and then right here is our initial compression distance from equilibrium. We'll call it X. That's given to us as 0.5 meters. Okay, and then let's redraw the diagram for the end of the problem when we stretch the spring on the other side of the equilibrium position. That's right here. Okay, so here's the equilibrium position. We end up with a final speed of 0. Once again, let's draw the surface here like so. And now here's the unknown, how far we're displacing the spring on the other side of the equilibrium position. I'm going to give this a name. I'm going to call it x prime. So x prime is the unknown. When we do eventually find it, we expect it to be a little bit less than 0.5 meters because some of the energy is lost as heat. Okay, and now we just set up our expression. So we're going to have here, first of all, work done by kinetic friction equals change in kinetic plus change in spring potential energy. There's no change in height here, so I don't have to worry about any changes in gravitational potential energy. And now we just start filling in our terms. So first of all, in the first term on the right-hand side of the expression, both the initial and final kinetic energies are 0. The object starts at rest and it ends up at rest. So then the delta K term here is 0 minus 0 for that reason. And now we have changes in spring potential energy. Our final spring potential energy depends upon how far we're stretching the spring here on the other side of the equilibrium position. So that's 1/2 k x prime squared. And then minus the initial spring potential energy when we initially compress the spring the distance x. So then minus 1/2 kx squared as the initial spring potential energy. Notice, by the way, if there was no friction in this problem, the left-hand side of the expression would be 0, and then of course x prime and x would be the same value. That would be a simple harmonic oscillator, which we've already covered. But now we do have kinetic friction, of course, in this problem, so I have to calculate the work done by it. This involves drawing out my force diagram. When I draw my force diagram, however, I'm going to ignore the spring force. The reason why is because we've already taken care of it here with the change in spring potential energy term. So just think of it like this. The object slides from left to right in this problem. So then therefore, vertically we have the normal force and gravity just canceling each other out. And then opposing the motion, which is to the right-hand side in this problem, opposing the motion like so is the force of kinetic friction. Notice that I did not bother to draw in the spring force, once again because we've already taken care of it here with the change in spring potential energy term. Okay, so let's go ahead and do our dot product now. Okay, so the work done by kinetic friction is our dot product between kinetic friction and the displacement. Okay, as is always the case, here's our 180-degree angle between those two vectors. Cosine of 180 is -1, so we pick up our negative sign, like so. Okay, the force of kinetic friction is the coefficient multiplied by the normal force. And then for this horizontal problem, the normal force is equal to the object's weight. Like so. And now before I take this expression and plug it here into the left-hand side of the equation, we have the displacement delta r. What is the delta r displacement over which friction acts in terms of the other variables in this problem? Notice it's the following distance. It's x plus the unknown x prime. So let's go ahead and substitute that into here for that reason. Like so. Okay, there's my expression now for the work done by kinetic friction. That's then what goes into the left-hand side of our equation. So let's go ahead and plug that in now here on the lower board. Okay, so work done by kinetic friction, like so, equals then the right-hand side of the expression. I'll toss away my zeros. Like so. And now x prime is the unknown. So what do I have to do to solve for x prime? Well, notice that right here is an x prime squared. This then means that I'm going to have to set up a quadratic formula. So because of that, this is somewhat of a messy problem. I'm saving it here for the end of this section on non-conservative forces. So let's go ahead and do the remainder of the algebra. Once again, we need to solve for x prime. So let's first of all go ahead and distribute the terms here on the left. Let's do this first. Like so, and then here's the right-hand side. Like so. Okay, and then let's go ahead and take these two terms here and move them to the other side of the expression. When I do, we're going to end up with our quadratic equation. We'll then solve for x prime using quadratic formula. But first of all, I have this term here, like so. And now let's take this term and move it to the other side so it becomes positive, like so. And then I have my other two terms. Take this guy and move that to the other side, like so, and then I have this additional term, like so. So take a look at this carefully. Okay, and now here are the coefficients when it comes to setting up our quadratic formula. Right here's the quadratic term. So the 1/2 k is our coefficient A in quadratic formula. Here's the linear term. So these guys right here is the coefficient B. And then keep in mind that all of this stuff here that I've isolated in parentheses is known. All of theirs are constant. This right here is the coefficient C in quadratic formula. And now we just plug everything in to ultimately end up with our result. Okay, so let me go ahead and do that here. All right, so setting up quadratic formula, we're solving here for x prime. So first of all, we have -b, like so. And then plus or minus, so somehow two answers. We're going to have to interpret that as we reach the end of this process. Okay, and then we have the square root of, first of all, b squared minus 4 times A, and then all times C, which is this mess here in parentheses from earlier. Like so. And then all divided by 2A. Like so. So let's take a look at this carefully. Let me make sure that I did this right. So negative b plus or minus a squared of b squared minus 4 times a times c divided by 2 times a. Okay, very good. All right, let's go ahead and simplify and then start plugging in our numbers. Let's get rid of this junk. Okay, so first of all, down in the denominator, the 2's cancel out. Let's get rid of that. And then up underneath the radical sign, this 2 here is going to cancel with a 2 out in the front like so. And that's about all that I can do for simplification. And now let's go ahead and plug in our numbers and let's see what we obtain. Okay, so the first term is negative 0.3 for the coefficient, multiplied by 1 times 9.8. So this ends up being about negative 2.94. Okay, plus or minus. And now I'm going to do the radical. So I got this guy squared, so let's square that. Okay, and then minus 2 times 100, so minus 200, and then times the following quantity. 0.3 times 1 times 9.8 times 0.5. 0.3 times 1 times 9.8 times 0.5 minus 1/2 times 100 times 0.5 squared. Quantity equals, take the square root of all of that, equals 47.06. And then all divided by k, which is 100. And now we have two answers, as I said earlier. Notice, however, that if I use the negative sign here in the numerator, one of the answers will be negative. I toss that answer out. The reason why is because you have to remember that ultimately everything that we've done here comes from dot products, which gives you magnitudes. So this right here is not a position vector. It's a distance, it's a magnitude, so therefore it's a positive number for that reason. So we just toss out the negative answer, it has no physical meaning. So then therefore my final answer now is going to be negative 2.94 plus 47.06, and then all divided by 100. And I end up here with 0.44 meters. Notice that this is a perfectly reasonable result. It's slightly less than the original compression distance of 0.5 meters because the energy has been lost as heat, or some of the energy rather, has been lost as heat. When you go through a really long, laborious algebraic calculation such as this, you arrive at your answer and you say to yourself, okay, is this answer reasonable? Absolutely. So then therefore, because it is reasonable, we probably have done the problem correctly. Okay, this concludes this section on non-conservative forces.